This is an example application for flow control valve. This circuit is known as the meter in circuit. You can see the meter in circuits are typically the flow is controlled before the cylinder. So you can see this cylinder, there is a flow control valve here. So flow is controlled here. On the meter out circuit, the flow is controlled on the return line. So if I run the simulation, um, it is still running the simulation. However, I think it's going very slow. So if I go move that, no, it's not running. Let's see what's going on. So let's run it again. So you can see that. Let me change that flow control, um, the speed. So I'm just going to make it a little bit smaller so we can see what's going on. So you can, if I engage there, you can see this is moving. Now I can change this flow control like that, and it almost going to very slow. If I go move all the way, it's going very fast like that. So I can control these the control valve setting, and then I can actually control the speed of this cylinder. So it is used for controlling the speed. So right now it is moving, but it's moving very slow. However, if I increase it, it will change. Now let me pause it. Now, as you know that there is no direct way of measuring flow. So the way it is measured is we set two pressure gauges before and after the flow control valve, and then we use some equations to get the flow on this line that is going into the cylinder. And we can perfectly control whatever flow we want, and that will control the cylinder speed. So let me go and show you how to use how to do the calculation. So for a flow control valve, whether meter in or meter out, it's the same equation. So for any flow control valve, the equation for that is the flow control valve coefficient or constant times delta P divided by specific gravity and square root of that. Now, delta P in this case, we have 78.345 bar. I have converted that to 1136.35 psi, and I have converted this 0.34 bar to 4.9 psi. So then you can put it here. Let's assume that the flow control valve coefficient is 1.5 or something. So let's do 1.5 is square root of this 11.3.35, 1136 psi minus that 4.9 psi divided by specific gravity. Let's think about something like motor oil. It has a specific gravity of 0.9. So let's use 0.9 there. So I have got that, and this will come in gallon per minute. I got 53.18 gallon per minute. So that's my Q. If I want to calculate the velocity, then that would be Q by A. I can convert this Q right here, maybe gallon per minute to inch cube. So I know that 1 gallon is 231 inch cube, and then 1 minute is 60 seconds. So I can convert that way. So if I plug all this number here, let's assume this cylinder is 4 inches of diameter. So the piston diameter is 4 inches. So if I plug in all this number, 53.18 times 231 divided by the area, which is pi by 4, d square 4 inch times 60 second. This was in inch cube. Now how is inch cube on top and inch square. So eventually this will come in in inch per second. So I got 16.29 inch per second. Now if I convert that 16.29 inch per second to foot, I know that 12 inch is 1 foot. So then I got that 1.336 feet per second. So the idea of flow control valve or meter in or meter out circuit is to control the speed of the cylinder. So if I want to go very slow, I will restrict the flow here, decrease the flow, because I know that velocity is Q by A. So if I decrease Q, then the velocity will decrease too.